Hello, thank you for joining me today. I'm Deepanshu. I'm a graduate student at U of T, and I'm going to be talking about the formula complexity of the subgraph isomorphism problem and how it relates to this graph invariant known as tree depth. This is joint work with Ben Rossman, who is at Duke. So let's look at the definition of this problem sub G, also known as the colored G subgraph isomorphism problem. So say you have a graph G. In this problem, you're given as input a graph which is known to have the following structure. So every vertex in this input graph belongs to one of these color classes. There's one color class corresponding to each node of G. You also know that the only edges in your input graph, they go across these color classes. And you also know that each of these color classes has at most n vertices each. And you're supposed to figure out if your input graph has a properly colored copy of G sitting inside it. So in this example, indeed there is, as I've highlighted here. Right, so now let's look at the models of computation that we're interested in. So these are going to be Boolean circuits and formulas. So what is a Boolean circuit? It's simply directed acyclic graph whose nodes are labeled by and or not gates. And formulas are special classes of circuits for which the underlying graph is a tree. And here's a picture of a formula. And NC1 is the class of polynomial sized formulas. We would also be interested in a restricted class of formulas, so which are called AC0 formulas. These are the ones in which you allow for unbounded Fanon and or not gates. However, you only have bounded depth. Now let's talk about a couple of special cases of sub G. So the first is when G is a clique of size K. This is also known as the K-clique problem, and its complexity is intrinsically tied to the P versus NP problem. The second one is when G is PK, so that's the path of length K. This is basically the same as the distance K connectivity problem, or the parametrized version of the ST connectivity problem. And its complexity is tied to the NC1 versus P problem, which is really the problem of distinguishing the power of formulas in circuits. And I quickly want to mention that a lot is known about the circuit complexity of both these problems in restricted settings. So you have all these monotone and AC0 circuit lower bounds for K-clique as well as for PK. And I'm just flashing a few of them over here. All right, so what is known about the complexity of the general problem, sub G? So here's what we know. So there are these simple to construct monotone AC0 circuits, which have size n to the roughly tree width of G. And you have monotone AC0 formulas, which have size n to the tree depth of G. I haven't defined tree width and tree depth yet, so we're going to see the definitions in a moment. But I just wanted to mention these early because I'm going to mention our result early on. So first, let me mention this result of Lee-Rasberov-Rossman. So that provides a circuit lower bound in these restricted settings. So in both the AC0 and monotone settings. They show that circuits computing sub G require size at least n to the tree width divided by log tree width in the exponent. And I'm going to hide the log factor in this tilde notation. And what we show is basically a result that complements this Lee-Rasberov-Rossman result. We show it for restricted classes of formulas. So we show that any AC0 or monotone formula solving sub G requires size at least n to the something, and that something is a polynomial in the tree depth. All right, and now let's talk about the conjectures. So what is conjectured is that the unrestricted circuit complexity should be at least n to the omega tree width of G. This, of course, would separate NP from P. And this is a fine-grained complexity conjecture. And you have an analogous situation for formulas. You conjecture that unrestricted formulas require size n to the tree depth. This would, of course, separate P from NC1, and even NL from NC1 via the ST connectivity problem, which we know is complete for the class NL. And this via the K-click problem. All right, and there is some evidence for this circuit conjecture. So Daniel Marks a few years ago showed that ETH, the exponential time hypothesis, implies that unrestricted circuits solving sub G indeed require roughly n to the tree width of G size. All right, so now let's talk a little bit about tree width, tree depth, and then graph minus. So tree width is a graph parameter that simply measures how tree-like your given graph is. So tree width of any tree is 1. And just as an example, tree width of the clique of size k is k minus 1. And here's a picture. So how do you define tree width? Well, you look at a certain tree decomposition of G, and you define tree width to be the width of the tree decomposition. So I'm not going to get into the details, and the precise definition of tree width is not really important for the rest of the talk, but just to mention it very quickly. However, tree depth is slightly less well known, so let's see that in a bit more detail. So tree depth is a parameter that measures how star-like your graph is. So tree depth happens to be 1 for a union of stars. All right, so here's the definition. So suppose you have a rooted tree T. You define its closure by simply including all the ancestor-descendant pairs, right? So the ones in red in this picture. And you define the tree depth to be the minimum height of a tree such that your graph sits inside the closure of that tree. Right? So for example, you have the clique of size 4. As we can see, its tree depth is 4. For the complete binary tree K33, it's again 4. And for parts of length k, it happens to be log k. So for P7, the tree depth is 3. And yeah, we know this relationship between tree width and tree depth. So you have, well, you know that the tree depth is at least as large as the tree width. And you also have this upper bound. But for the rest of the talk, the thing to keep in mind is this first half of the inequality, that tree depth is simply larger than tree width. Right, so now let me state our results slightly more precisely. So first, let's see the Lee-Rasberg-Rossman results again. So it says that for all graphs G, the circuit complexity of sub G is, well, the restricted circuit complexity of sub G in these settings, AC0 and monotone settings, is n to the roughly tree width of G. And our result is it complements this result in the following way. So we say that the formula size of sub G in these restricted settings is n to the tree depth to the 1/3. It's a polynomial in the tree depth in the exponent. All right, so now I'm going to make a bit of a digression and talk about graph minus. We'll see in a moment why they are relevant. So a graph F is a minor of a graph G if it can be obtained from G by a sequence of deletions and contractions. So here's an example. You start with this graph G, you delete these edges, and you contract these edges to eventually land at this triangle. That's F. So in this situation, you would say that your graph G has a triangle as a minor. And what we also know is that tree width and tree depth, so the two parameters defined earlier, they're both minor monotone. Right? What does that mean? It means that if F is a minor of G, then the tree width of F is at most the tree width of G, and the tree depth of F is at most the tree depth of G. All right, so now let me talk about graph minor approximation. This is simply an attempt to approximate a graph parameter using graph minors. So first, let me state this, I guess, rather well-known result. So it's called the polynomial grid minor theorem for tree width. This is not going to be directly relevant to us, but okay, so it says that every graph that has tree width that's at least some polynomial in K has the K by K grid as its minor. But what's going to be relevant to us is this tree depth analog to this theorem. Right? This was proved by Kobayashi, Rossman a couple of years back, and then improved recently by Chervinsky, Natara, and Piripchuk. And this was by Chakuri, Chuzor, and Chuzor-Tan in a sequence of work. All right, so what does the tree depth analog say? It says that any graph that has tree depth at least K cubed must satisfy at least one of the following. So either it has tree width itself that is larger than K, or it contains a path of length at least 2 to the K, somewhat large, or it contains TK as a minor. So what is TK? Well, TK is the graph that is the complete binary tree of height K. Okay, so why is this second theorem relevant to us? Well, it allows us to reduce the problem of proving lower bounds for the general sub-G problem to proving this sort of a lower bound in each of these three cases. Right, so an n to the omega tilde K. So in the first case, it's tackled directly by the circuit lower bound that we have from Lee, Rasberg, Rossman. So obviously the formula size is at least as large as the circuit size. The second one is tackled by this result of Rossman a few years ago. And the third one is really the content of our work. All right, so just to state it again, slightly differently, this is the main technical result. We said that the complexity of sub Tk, the restricted complexity of sub Tk, is at least n to the omega k. And let me also mention that this lower bound for the case Tk is obtained in the average case, right? So for a generalization of Erdős-Rényi graphs. So of course, at this point, you can ask, well, what is the input distribution for which we obtain these lower bounds? And let me just describe that very quickly. So here's a picture. So your input graph, it looks like this, right? So you have these color classes corresponding to each node of Tk, right? And sitting inside each of these cookies, yeah, is n vertices, right? And then across these, across an edge of Tk, yeah, and for any pair in this graph, you pick that edge with probability. Well, for the top vertices, you pick it with n to the minus 5 over 6. For the internal nodes, you pick it with n with probability n to the minus 2/3, and for the ones at the bottom, you pick it with n to the minus 4/3. So these numbers, they're not particularly mysterious. They simply come by choosing these probabilities such that the probability of seeing a Tk via this random experiment is bounded away from 0 and 1. All right, so now let's talk about the lower bound proof techniques. So here's the main technique. Right? So we're going to use this lifting theorem from a result of Rossman a few years ago, also known as the part set framework. So what you do is you reduce the problem of showing lower bounds, restricted formula lower bounds for sub G, to showing lower bounds on a simpler complexity measure that's defined on these combinatorial objects that we call joint trees with graph G. And so it is in this sense that these lower bounds, these sort of simpler complexity lower bounds, they lift to restricted formula lower bounds for sub G. Okay, so what are these objects joint trees? Right, so here's a picture. A joint tree is simply a binary tree whose leaves are labeled by the edges of G. And these edges, they sort of combine at the internal nodes to give rise to subgraphs of G. It's as depicted in the picture. Right, so what is the complexity measure that we prove lower bounds for joint trees, as I just mentioned? So what we really show is a lower bound on a certain potential function, phi. Right? So we show phi of A for all joint trees A with graph Tk is something that's at least linear in K. And this somehow helps us in establishing a restricted formula lower bound on the complexity of sub Tk. And this potential function phi is governed by these two rules. So here they are. This is the dagger and the double dagger rule. I'm not going to get into the details, obviously, but what I do want to mention is that the technical core of the paper is just trying to use these two results somewhat cleverly to establish this linear lower bound. And this turned out to be a really fun, but also challenging combinatorial problem. All right, so now let me switch gears a bit and talk about some supplementary results that we have. And these are going to be formula upper bounds for a specific case of sub G. So it's going to be sub pk. So that's the path of length k. And it's rather going to be the average case version of sub pk. Okay, so what is the average case sub pk problem? So imagine you have this layered graph on k plus 1 times n many vertices. Right? So each layer has n vertices. And across any layer, for any given pair of vertices, you include that edge with probability that's roughly 1 over n. And then once you're given such a graph, the problem is to determine if there's a path that goes all the way across. So that starts at 0 and ends at k. So in this example, indeed there is, as highlighted here. All right, so we're going to solve this problem, right? So remember, we're talking about formula upper bounds. So what is a simple algorithm for this? So we can apply this recursive doubling technique, right? Which is basically a divide and conquer approach. Right, so you look at the middle layer, you see if there's a path going from first to the middle layer and then middle to the rightmost. And if you've seen the proof of Savage's theorem, this is exactly how that proof goes. So Savage's theorem, it relates the non-deterministic space complexity to the deterministic one. And turns out that this recursive doubling technique, it can be implemented using De Morgan formulas of size n to the log k. And now I claim that this can actually be improved. So you can actually get formulas solving average case sub pk of size n to the half log k. Okay, so how does this work? So you start off by picking random blocks of indices, right? So you pick roughly square root n many blocks of size square root n each. And just to emphasize, these are indices. So they're not dependent on the layers. Right? And then you have, you define roughly log n many formulas, which for a fixed block on the left and on the right, they tell you the following. So if there is indeed a path that starts at the left block and ends at the, so it starts at your given block on the left and ends at the given block on the right. These formulas, they tell you, first of all, if there is a unique path like this. And moreover, they tell you what these end vertices are as well. Right. So, okay. So how do you construct these log n many formulas recursively? So again, it's going to be a divide and conquer approach, and you do it in the following way. Right. So for all possible choices of blocks in the middle layer, you check if there's a unique path that goes across, right? Something like this, and if there is one, then you're going to get the vertices. The end vertices. And you also know this from the middle to the right. And then in the merge step, you just check if basically these two vertices are the same. If they are the same, you output yes, and otherwise you output no. Right? And then you do this for all possible choices of these blocks at the end. And this gives you what you want with high probability. And turns out if you work this out, the formulas have size m to the log k, right? So m was the number of blocks that we picked, which, as I said, was roughly square root n. Right, so this recursive doubling algorithm can really be seen as a join tree, right? So this is, it corresponds to this join tree, right? So I'm only going to talk about this vaguely, but here's the correspondence. So yeah, you start off with a path of it's a length k, and you have these subjoin trees which have length k over 2, k over 2. And these subjoin trees, they correspond to these paths, right? And these paths, they intersect at this one point. And yeah, as we just saw, these correspond to formulas of size n to the half log k. It turns out that there's a completely different algorithm for solving the same problem, which sort of corresponds to this join tree, right? So instead of sort of minimally overlapping your subjoin trees, you try to overlap them maximally. Right? So you have, so as your subjoin trees, you have paths of length k minus 1 on the left as well as on the right. So kind of like this. Turns out this completely different approach also gives rise to a different n to the half log case size formulas for average case sub pk. And what was surprising is that this is not optimal. So you can actually improve this to n to the something that's got to do with the golden ratio, interestingly, and that's smaller than half log k. And these turned out to be, yeah, by picking the Fibonacci numbers, yeah, which was rather beautiful. So this is how we were able to improve the n to the half log k formula upper bounds. And we also have some reason to believe that this constant might actually be optimal, because we ran some MATLAB code and solved some linear programs. So let me just end by mentioning a couple of open problems. So presently, the best known formula upper bounds, as we just saw, is this this term here, which has a log k with base square root 5 plus 2 in the exponent, whereas the best known lower bound, restricted lower bound, which is another result of our work, shows that it's square root 5 plus 5 in the base of the logarithm. So the natural question is, can you close this gap completely? And of course, it's open to improve the restricted formula lower bound from n to the tree depth to the 1/3 to simply n to the tree depth. I do want to point out that such a result then cannot rely on the graph minor approximation theorem, so for tree depth that we saw earlier, because we know that there has to be a quadratic cubic loss if you use that. And then finally, it would also be interesting to establish this lower bound, just in the case of tree patterns. So Yes, thank you. That's it. That's my talk.